Hello again, RadioWave students. We will continue. This is an example on flat Earth. It is a comprehensive example where we will calculate the electric field at a distance at the receiver location. The operating frequency is 1 gigahertz. The next example will be about the electric field. Here only flat Earth example to find maximum distances. The frequency here is 1 gigahertz. The transmitter height is 21 meter and the receiver height is 18 meter. The question is find the locations, the farthest 3 locations of the receiver to receive a maximum radiation. To receive maximum radiation, since it is a flat Earth, this path gain factor should be a maximum. The maximum value of it will be 2 because the maximum value of the sun is 1. Here, if you cancel this with this will be 1 here. Sine is equal to 1. The argument should be pi over 2 plus n pi, where n is equal to 0, 1, 2, etc. This is the argument. Take this is the argument, the angle here. The distance d here, if you take it to this side, and you cancel the pi with the pi with the pi, is equal to this quantity. This quantity 2h1 h2 over lambda naught divided by 1/2 plus n, because it will go to the other side. We substitute for h1 is 21 meters and h2 is 18 meters and lambda naught is, for 1 gigahertz it's 30 centimeters, the wavelength, or 0.3 meters, and we obtain this here equation. D is equal to this. D is maximum when n is minimum. N is minimum means n is equal to 0. When you put n is equal to 0, the maximum distance is 5040 meters. That's part A. Now part B, find the 3 farthest locations for no radiation received. There is radiation, but we do not want to receive radiation. This means that the path gain factor is 0 and sine is 0, and the angle should be n pi. Sine n pi is equal 0. Cancel pi with pi, and d, if you take it to this side, if you interchange d and n, d is equal to h1 h2 over lambda naught n. Here h1 is 21 meters, h2 is 18 meters, and the lambda naught is 0.3, and n here, minimum n is, to obtain maximum d is 1. It is 1. If you want another distances, you will put n equal 2 and n equal 3. So it is 2520 meters, around 2.5 kilometers. The third problem, part asks for, or if the distance is 2 kilometers, if the distance is 2 kilometers on the Earth, find the minimum 3 heights of the receiver. The minimum 3 heights, the distance is given. Now to find the minimum 3 heights of the receiver, h2, height of the receiver, to obtain the same radiation as that of a free space, when the range is 3 kilometers. Therefore, this is RF, this is free space range, and this is D. This is part C. F over D equal 1 over RF. D is, we said it is 2 kilometers and RF is 3 kilometers. F is equal 2000 over 3000, 2 over 3. This is equal to sine K naught 2 times H1 H2 over D, absolute value. Now cancel 2 with 2, and the sine is equal 1 over 3. When the sine is equal 1 over 3, here we have absolute value. Okay. The argument 2 pi, the angle 2 pi over lambda naught times H1 H2 over D should be equal here, plus or minus, should be plus or minus. Plus or minus 0.339 radians. This is radians. Radians. Okay, plus n pi. And if you cancel here, if you substitute the values of H1, H2, lambda naught, you will obtain this equation here. But this here should be plus or minus again. Plus or minus. And H2 is equal to minimum. For n equal to 0, we have the positive value only, of course, this value. For n equal 1, I think here we have two values. We have another value here. You can calculate it. Okay. The other value will be minus, here this value will be minus point minus 0.34. Here it's approximately 3398 is 34 plus pi, n is equal to 1 plus pi. Okay, all are multiplied by lambda naught is 0.3 meters, 30 centimeters, times 0.3 okay, here we have, this is times 0.3 times distance d. Distance d is given in the third part. Distance d is 2 kilometers. In part C it is 2 kilometers. Part C it is 2 kilometers. Distance d is 2 kilometers. Okay. Distance d is 2 kilometers. Times 2000 meters over 2 pi H1. H1 is, how much was H1? The transmitter height, H1 was 21 meter. H1 was 21 meters. Okay, times here 21 meters. Point minus 0.34 plus n is equal to 1 pi times lambda naught 0.3. Distance is 2000 meters, 2 kilometers, and 2 pi h1 is 21 meters. Using the calculator we can find this. Let's calculate this again. This is 0.34 times 0.3 times d is 2000 divided by 2 divided by pi divided by h1 is 21 meters. We obtain the same answer, 1.546, 1.545. Depends on the, because here we have used the exact and here we have used the approximate here. Here 0.34 minus sign plus pi equal times 0.3 times 2000 divided by pi and divided by 2 times 21 is 42. The answer is 12. Here we will have an answer. Here it should be 12.74. 4 meters. The three lowest heights of the receiver are 1.545 meter, 12.74 meter, and 15.83 meters. Okay. Now the last example involves using Fry's transmission formula and the electric field. We have transmitter that has a height of 80 meters and the receiver height is 10 meters. The distance between the two is dt. If you calculate dt, it will be 8.1 miles. The gain of the transmitting antenna is 5 and the transmitting power is 500, or the power transmitted is 500 watts. The frequency of operation is 100 megahertz and the wavelength is from this is 3 meters. It is required to find the electric field at the receiver location. We want to find the electric field. The strategy of solution here is to find the free space range. If we find the equivalent free space range for this problem, we can use Fry's formula to find the electric field, because in free space we know that the power density, radiation power density, is 1/2 electric field squared over the intrinsic impedance of the medium free space. So let's start here. To make sure that we can use flat earth formulas, we calculate dm square root of twice AEH1 plus twice AEH2 in miles. This is another formula. This is in kilometer and this in miles. This is in kilometer or in meter, and this can be written in miles if you put H1 and H2 in feet. So the distance is 30 miles dm and our distance is 8.1 mile. 8.1 mile is less than third of 30 miles. Therefore we can use flat earth. From here from this. The third is taken from here. Flat earth is used when d is greater than d max and less than 0.3 dm. dm is 30 miles. 30 times 0.3 is 9 miles, and our distance is 8.1 miles. Therefore we can use this formula, and of course d is greater than d max because d max will be here. Therefore we can use here F is equal twice sine k naught 2 pi over lambda naught h1 h2 over d. When you substitute, h1 is given, h2 is given, d is given, lambda naught is given, and F is equal 0.25. We know that F is equal d over Rf because F over d is equal 1 over Rf. F over d, this is the power proportional to the voltage received when we have flat earth, and when we have free space, the voltage received will be proportional to 1 over Rf, the free space range. This is R, not V, this is R. Okay, let's write it. Rf, Rf. Okay, now this is 0.25. F is 0.25 here, as you can see here, 0.25. If you reverse this fraction, Rf is equal, the reverse of this is 4, therefore Rf is equal to 4d. Rf is equal to 4 dt for distance. The distance is 8.1 miles or 13 kilometers here, 13 kilometers. Therefore our free space range is 4 times 13 kilometers. When we use the free space range, we can use this formula. The power density is 1/2 electric field magnitude squared over Z naught. Z naught is 120 pi, 377 ohm for free space. This is from Fry's formula, is transmitter power divided by the surface area of the sphere with a distance of 4 dt, because Rf is 4 dt squared, times the gain in that direction. This will give us the power density at the location of the receiver. Now the gain is given, the power transmitted is given, and dt is given. Z naught is known, 120 pi ohms, and we can find from this equation E. Here you can see Z naught is 120 pi ohm intrinsic impedance of free space, and PTC 500 watts, and gain is 5. It is a ratio, and 4 pi, and dt is 13 kilometers. It's given in the question, and we obtain E. E turns out to be 7.4 millivolt per meter. That's the end of this session, and we will continue later on. Thank you for listening.